So anyways, let's review a little bit. So today is going to be a lecture. There's not going to be a lot about research. It's going to be about neural networks and the core concepts in artificial intelligence. We'll use them in research in the third lecture on Thursday. So what we've seen so far, and I'm going to do a review very fast, is that we are, in a way, trying to find the difference between interpretable science, where you assign meaning to the variables and eventually describe mechanisms, against data-driven science, where you have non-interpretable black boxes that you train in order to obtain results. And I've shown an example of interpretable science where you have a dynamical system derived from basic equations. You find the qualitative different behavior. And if you do some magic trick that I encourage you to study, you can take that into a simpler, even simpler dynamical system with just the minimum number of parameters. And that would allow you to model your dynamics, because the qualitative behavior is going to be the same that you describe from basic phenomenological considerations. This is normal form theory, and probably the main things that you have to study in more or less simple dynamics, where simple would be up to some sort of chaotic dynamics, could be captured by normal forms and simple dynamical systems. And they can be even quite realistic. What I say is that if you do basic dynamical modeling, for example, you could tease the brain of a bird with synthetic songs and stuff. So Newton's mandate, what we have in our heads, what we've been studying in school for the last 5 years, in your case, or 6 or 7, is that in order to understand a problem, you have to unveil a mechanism that, for example, in case of a dynamical system would be a vector field. You put them into machinery, that is dynamical systems, linear dynamics, whatever, simulations of some sort, and you make a prediction. And the novelty of the 20th century is the theory of dynamical systems, where all these things can be done qualitatively. This is what we saw yesterday. But now, we were the ones that defined, for example, in our problem, that the motion of a labium was important in order to produce the sound. And some of you asked me, how do you make the sound out of that? So you have to know a lot of the basic science in your problem to say, well, of all the bird, with all these moving parts and muscles and stuff, go and measure the behavior of this tiny piece of tissue. That is the key to model dynamics. There's a lot of science when you say, I'm going to model the dynamics of X. A lot of natural science, a lot of knowledge of your problem. So you decide that that's important, and that means that it's interpretable science, because you find which are the variables. You say that there are things that are less relevant or can be derived from that. And you will write equations. But in many problems, it is not even clear which are the variables in terms of which you need to write the model. And some people clearly don't care about that. If someone wants to sell you something and wants to profile you in Facebook, they don't want to know why, if you like certain pages, you're more likely to buy a ticket to Tanzania. They just want to know that you will do it. They don't care about why. What defines a profile? Maybe sociologists analyzing your data could be interested, but this is not, in principle, what they worry about. They worry about selling you the trip to Tanzania, right? So in this scenario, let's say that you assumed that your dynamics is slow, fast, and so on. What people are having in mind is that instead of trying to unveil the vector field and the equations, let's try to train a device such that, looking at many examples, that means a pair of variables allow you to get to a next point in your dynamics, and you prepare a lot of examples. You do the training of some function that will, in principle, allow you to infer which will be the result of applying that function to a new point in your dynamics in order to predict the future. So what is this kind of machinery? Well, it's something very different than the things we've seen so far. And this is what I want to describe today. What I want to describe today is just two concepts. I wanted to get out of here with two concepts: the universal approximation theory and backpropagation. Because every neural network you will face so far is based in these two concepts, okay? Okay. So is it possible to find this function? Why does it work? So the battle between interpretable science and training with example is not restricted to dynamics, complicated science, and so on. I'm going to show you an example of my phone. And in your phone is the same because we're living through a phase transition in science and technology. So half of your applications probably come from interpretable science in a way, and half of them from this new paradigm of artificial intelligence. So let me show you one example in my phone, because since you know, I like birds. And in the last years, I've developed the hobby of doing bird watching. So I have two applications that I use a lot. This one is called Aves Argentinas, and this one is called BirdNet. So Aves Argentinas has a traditional programming, and BirdNet is fed by Terminator, if you want. This is artificial intelligence. What do they do? In Aves Argentinas, you are asked several questions. Which is the size of the bird? Which are the colors of the feathers? And so on. How is the beak? How large is the beak? And depending on your answers, it will give you some possibilities. There was a scientist there that knew that if you have a family of the passeriforms, you have so many families, and in each of these families there are so many species, and each species has all these particular features. So someone knew which are the important variables that are these things, and they had some knowledge of how these variables map towards a particular species. This is the typical case of interpretable science. Now, what does BirdNet do? BirdNet computes a sonogram that is a visual representation of the frequencies of a song. So what happens is the following. You have the sound signal. You pay attention to small temporal windows, and you compute the spectral content of each window. And then you plot, graded with a scale of colors, the frequency in the vertical axis as a function of time. So for example, in here, what you have is a song. In here, you have a song. And you have like some spots in here that corresponds to syllables going up, then a rapid trill. If you remember, yesterday, I've shown you this particular song at some point of the talk. But the code doesn't have any idea of this. What it does is processes this image and sends it to a neural network that has been trained that a pattern with these features, a pattern like this will give a high probability of a particular species that is Sonotrichia capensis. No one fed particular information on which are the particular frequencies here and so on. They've shown the network many examples of images that corresponds to songs of the same species, and they said in all these cases, it is Sonotrichia capensis. So we'll see how you do that, and how you can achieve that, and how you can modify the parameters in a network in order to achieve this result. So BirdNet translates sound into images, sends the information to a fitted function that was trained to classify, and the result is then sent to you if you have a 4G connection or a Wi-Fi connection to your phone. Actually, the network is run in some servers in Germany, in Göttingen, people that collaborate with Cornell University, and they have been training this for the 10,000 species that exist over the last years, and they are very successful in classifying these things. So what is inside the brain of this classifier? So as I was saying before, you have a sound, and then you compute the spectrogram that is using these Fourier transforms in Windows, and you have a visual representation that translates the acoustical features of your sound into an image, okay? Now, what you want is to build a function such that your input is this matrix of colors. So this is a matrix, right? You have certain number of pixels here, a number of pixels here, and then you codify between 0 and 256 the levels of gray. So this is an image, it's a matrix. So the function of this matrix has to be a probability of the bird belonging to a given species. So I want this function to be such that if the input is the sonogram, then the probability of this being Parus major is very high, in this case, 97%. Now, which is the device that allows you to do that? Well, the star of artificial intelligence are neural networks. So neural networks are these devices where you have many units, and each of these units is a computational unit. And if you want to understand what I'm talking about, think of an Excel page, a spreadsheet, and then one of the cells, that's a neural network. And when you say that you're going to code, well, what you say is that in a column, I have all these cells. So the formula that's going to give me the result for that cell is some nonlinear operation of a sum of the outputs of the previous cell. That's a neural network. There is nothing more interesting than that. In this case, it's a feed-forward network. Every layer has connections to the next layer. There is not back propagation, so this is very different to a real network of neurons. And as opposed to real neurons that can be excitatory, inhibitory, and they spike and so on, they are just, cells of memory, and you're going to compute the output by computing the values of the previous cells. And the reasons for which you have this forward connectivity is because it was found to be, and we're going to see how, very easy to train. Okay, the first attempt to give cognitive properties to arrangements of cells was done by Hopfield, that won the Nobel Prize in Physics last year, and he had in mind a different device. He wanted to translate typical spin systems into flavors to compute excitations and inhibitions, and he wanted to show that with some degree of connectivity, you could have attractors, and that you could represent memories by these attractors. So he had in mind a very different device. And then Hinton came along with his disciples and also with Terry Sejnowski and so on, and devised more smarter networks. But it wasn't until Hinton realized that with the feed-forward propagation, feed-forward connection, you could easily train them. Those were like more or less tools. Actually, I was at UCSD 8 years after Hinton had left, and everyone told me, don't get into neural networks. This is a dead field. And everyone was so sure that it was a dead field. And Hinton went to Canada and was doing very, if you want, marginal research until Google had the tools to feed, with tons of data, these networks, and the technology allowed to build really significant networks. But the knowledge was understood pretty early in the game. Anyways, so this computational device is a neural network. You have a set of layers, and then of course, the first layer has to code the input of this image, and the last layer has to have a number of cells that corresponds, in this case, to the number of classes that you want to have as options. And the idea would be that one of them is going to give a value significantly higher than the others. You want to interpret this as probabilities, and therefore you want to say that your function took this image and told you that the probability of being this particular cell, that means this particular species, is very high. So the question, of course, is, can you always do that? Because the function that can understand that this is the song of the species, but then if you do another recording and you have this a little bit higher and a little deformed, also will give you the same result. It's not obvious that you're going to find function like that. So the two questions are, is it always possible to build this function? And second, can you train it? And the interesting thing is that if you understand this for this network, we're going to understand it basically for any neural network that is going around so far. Okay, and even Kolmogorov networks, which which are different than multi-layer perceptrons, are conceptually similar. So the main theorem that allows you to have faith that you can eventually do it is the universal approximation theorem that tells you that a feed-forward neural network with a unique hidden layer, this is even simpler, okay? Just one layer, made out of a finite set of nonlinear units, can approximate any continuous function in a finite range of the input with any degree of precision if the activation is nonlinear, continuous, and bounded in the domain. Okay? So it doesn't matter that you have a function very complicated. What the universal approximation theory tells you is that in a finite domain, okay, in a finite range of the domain, you will be able to approximate it with only one layer. So let's work with an example to see if it makes sense. Just to stay in the same page, when I take examples of activations, that means when you take the values of the cells in one layer and you want to add them up and apply a nonlinear function to compute the value of a cell in the next layer, I said that there were nonlinear functions. Well, these are two typical nonlinear functions. This one is called a ReLU function. It's a function that is 0 for x smaller than 0, and just x for x larger than 0. This is the ReLU function. And this is a sigmoidal function. For the people that were in the problem session yesterday, we were talking about this extensively, okay? And you can use also hyperbolic tangents and so on. But those are two linear functions, and this is maybe the most popular one, and I'm going to show you an example of how to use it to build a very different nonlinear function. So these are the activation functions, and the theorem says that, again, using a unique layer of units with activations that are nonlinear like this, you can approximate any continuous function. So let's build one of these combinations of units. Let's build one of these networks and see what kind of functions I can build. So I prepared this example. The output, which is going to be this unit, so I'm going to have an input that's going to be a variable. I'm going to be processing by this one layer that the theorem is talking about, okay? And I'm going to have an output. And I want this output to be a nonlinear function of the input, and I want a nonlinear function that is not trivial, or at least that is not trivial to me, that you can approximate it with this kind of units. So my function is 20 times a ReLU function of minus x minus 1 plus 5 times the ReLU function of x plus 1 minus 5 times the ReLU functions of x, and this weird combination. How many parameters did I need? Well, I didn't need many parameters. I needed to know that this is a minus 1, and all these were 1s. And I needed to know that I had some biases in here that are the numbers that are coming in these arguments in here. It doesn't look like it's very complicated to find in terms of the number of parameters, right? So, of course, if I ask you, do you have any idea what this function is all about? You will say, no way. Doesn't make any sense, right? But if we look at it, it's this simple nonlinear function. So this nonlinear function, which is x cubed minus some coefficient of x, so this is a continuous nonlinear function of a nonlinearity completely different than the one of the activation units, was built as a combination of these very simple nonlinear units. Let's see how it worked. This is just one simple example. Oops. One simple example. We have the ReLU of minus x minus 1. Let's remember what the ReLU function was. A function that was 0 for x smaller than 0 and x for x larger than 0. So when I have ReLU of minus x minus 1, the argument is going to be 0 when minus x is equal to minus 1. That means when x is equal to minus 1. And then what I have is that since I have a minus in front of x, The interesting part is going to be when the argument is negative and not when the argument is positive. That is the reason why here I have that this piece is with negative slope, is 0 at x equal to -1, and then it's completely 0. So now I have this piece of this nonlinear function fitted. I have to fit the next segment. So for the next segment, I use a ReLU function that is going to be 0 at x equal to -1, and is going to have the interesting part for positive parts of x. And then I have this little piece in here. And I continue doing this, and I fit this non-trivial, nonlinear function as a sum of units that have this nonlinearity in particular. This is a universal approximation theorem, and is the hardcore mathematically for these functions being able to be approximated by layers of finite units coupled in a feed-forward way. Of course, if you start to add layers, then it's even simpler to approximate this. And let's see how this device would work if I have a classification scheme. So I will have an image. I will have a number of units that correspond to the input. I will have a hidden layer. And if I want to classify, I want to have as a final layer a number of units that corresponds to the number of classes that you decided you were going to use for classification. So in here, you will get the probability of being the sonogram, let's say, of a finch, and here the probability of being the sonogram of a canary, okay? Now, the computation that's being performed in each of these units is very simple. For example, it could be a ReLU function or the sigmoidal function or any nonlinear function that you're going to be using. For example, in this case, the value of xg is going to be the application of the sigmoidal function to a sum of some weights to the values of the units in the previous layer. So here you're going to have parameters that are omega ij, okay, that you don't know what they are, okay? And the output here is going to be this nonlinear operation over the results of the previous layers, where the sigmoidal function, as we said, is this thing in here. Of course, the idea is that in principle, if you have some random number of weights, there is no chance that you're going to get the right thing. So the interesting thing is whether we can choose the weights so that this gives us a result that makes sense. Hold it for a minute. Before going there, I want to describe how to use this for making predictions. Instead of classification, for doing predictions of dynamics. Well, for doing predictions of dynamics, you could use it in the following way. You take the time trace, and in principle, if you have a time trace, you have the hope that if you have a segment that is large enough of data, finite, it's going to be an embedding. That means that if your phase space, you have some topology that is interesting, okay, the information of all the variables is captured by small segments of a scalar variable of one of the variables themselves. But let's assume that this is the case. So you have just one of the variables, and you can unveil the dynamics from there. So you take a segment, and your segment is fed in here. So here you have the values of your time trace in some consecutive number of instances, of temporal instances. And then what you want to do is to predict the coordinates of the system at time t. So if you have a long time trace, you can use little segments and say, well, when I have this segment of data, the next point is this. If I have this segment of data, the point is this, and so on. And then eventually you want to apply it to some piece of the data that you didn't use for the training, and you want to have a good prediction. So the same architecture can be used. It's not the smartest one to do this problem, but it can be done either for classification or for regression. In both cases, you can use the same architecture. But now the problem is how you use that to choose the weights in such a way that the answer is the correct one. And here comes the interesting part. This was a work. So I should read my slides first. So we trained the network, exposing it to several examples, And in each of these teaching sessions, we want to correct slightly the weights omega ij. So the question is how? The essence lies in using the difference in between the outcome that you anticipated with the parameters that you had at some point, with a specific set of parameters to inform their modification, aiming to reduce this disparity. That means you have a network with some set of parameters. You make a guess. Then you use the difference to correct all the values, and then you train again. Can you do that? So the person who was responsible for solving this is last year's Nobel Prize winner, Geoffrey Hinton. Now, interesting enough, no one wanted to say that they would give Hinton a Nobel Prize for an algorithm. No way. So they had to go back and find what was really physics about Hinton's work, and the closest they got is the work with Boltzmann machines, right? So you had Hopfield, who did a really interesting contribution for this, and then you had many interesting contributions. One, Hinton, together with Terry Sejnowski and another coworker, I don't remember the name, had this paper on Boltzmann machines, and they said, well, this is the reason we're going to need to Hinton. But actually, everyone knows that this is the paper that changed the history of neural networks and artificial intelligence. It's a paper published in Nature in 1986, okay? And to me, the reason for which really it wasn't the paper on Boltzmann machines, the one that awarded him the Nobel Prize, is that really that paper was mainly conceived by Terry Sejnowski. So had it been the case, Terry would have been a Nobel Prize awardee as well, and he wasn't. So everyone knew that Hinton had to have a Nobel Prize if it was on neural networks, but they didn't want to quote backpropagation because it's a simple algorithm, and we see that it's so simple that it's embarrassing. So how does this work, this very interesting backpropagating error correction algorithm? How does it work? So let's imagine that I have a network where this is the last layer, the previous layer, you have some input layer. So here you have the pixels of an image, and you have all the weights in here. They are random, and you want to have an output, and you get something else. And of course, it won't make sense. So how do I correct the weights so that the output is what I wanted to do? Okay. So let's say that we're expecting a value yj from a network. For example, I put the image of a bird, which is a zebra finch, and I want the class that says that it's a zebra finch to say 1, and all the rest to be 0. So this would be, in my example, 1, the rest of them would be 0. These would be the yj's, what I really want. And oj is the output that comes from the network when I feed it with the image with some random set of parameters, omega ij. So there is going to be an error, which is the difference between what I expected and what I got. This is the error. So I want to change the weights as long as the error changes with the weights, because I want the error to be a minimum at the right weights, okay? So what I want is that whenever I'm not in a minimum, I have a gradient, and that gives me some change in the parameters, okay? So now, how do I compute this thing in a network? And this was a brilliant idea of Hinton. First of all, forget about this wonderful Hopfield idea. Let's just try to make it simple. Let's look with feed-forward networks, because I know how to compute this, he said, if this is a feed-forward network. Okay, let's see how it works. The derivative of the error with respect to omega, that means why there is an error that changes when I change omega, is because I change the error when I change the output. And I change the output when I change the net input into this unit. And I change the net input into this unit because I changed omega j. This makes sense, right? This is the chain rule. So we use the chain rule. How can I compute these things, or can I compute these things? Well, it's very easy. The net input into the J unit, when you change a weight, will change in this way. You know that the net input into this unit is going to be the sum of omega ij times OI. So the derivative of the net input into J with respect to omega ij is just going to be the output of OY. This is interesting because this is something that I have it in my computer. In the previous thing, in the previous run, when the thing didn't work, I know which is the value of the output. So this is something I have. Cool. I don't have to worry about that. What about this? The derivative of the output respect to the net input into the J unit. Well, if I use this very simple nonlinear sigmoidal function, the derivative of the output with respect to the input is just the product of O, the output, times Y minus the output. This requires a little bit of derivative. You have to compute the derivative of O with respect to the net. It's going to be minus 1 over this square times the derivative of this. You rearrange it, and you find that that derivative is just that's a product. And this is wonderful, too, because you have O and you have O. So far, these two terms can be computed from the values of the network at the previous step. Trivial. And then this term in here is very simple, because if the output, the error, was the difference square of the expectation minus what you got, the derivative of this is just this linear term. This is, again, O, something that I have, and this is what I expected, so I have it too. So the way in which you are going to be driving the change of your parameters is given by three things that you know, at least if you are in the last network, in the last layer. So far, do you follow me? Does it make sense? Okay. Questions? Okay. So what if we are not in the last layer? Well, again, there is going to be a change in the error when you change the weights, because you have a change in O, a change in net, and a change in net when you change the weights. That's very simple. So let's say that now you have the last layer is this one here. Well, this is what we computed. This is what we had so far. Now, let's assume that what we want to correct is a value that is within the network, deep within the network. So if I change this weight that is deeper in the network, of course there is going to be a change in the error, because this change will modify O. So there is going to be a change because the error changes, because O changed. O changed because the net coming to 6 changed, and the net coming to 6 changed because omega 86 changed. So far, this is very similar. This we can compute. This we can compute. This guy is a little bit more complicated, because now the output changed. The output here changed when I changed this, because this changed, this changed, this changed, and this changed. Okay? Now, the error changed when I changed 06, because 01 changed, 02 changed, 03 changed, 06 and 04 changed. But if you compute each of these guys in here, you're going to find that this is going to be our famous difference between the output and what was in the target, Y1, and all the rest we know them. So all these things are tedious, but they involve only two things: the values that you have in the iteration you want to correct, and the outputs that you obtain in that iteration that didn't work. So you have a complicated and tedious set of terms that tell you, if I want to change specifically the weights in such a way that I get guaranteed that the error is going to be smaller, then you know exactly how to compute this change in the omegas, just knowing how the network failed in the previous iteration. So now, how would that work? I want given this image to obtain a result, for example, 1 and 0, because I'm sure that this corresponds to a species. So some specialist made a labeling of this problem. Someone had to be training this, and someone had to know the result that was expected. But he or she doesn't have to know anything about this, doesn't have to explain the frequency has to be in this regime, it has to be a continuous line, it has to be tonal. No idea. I just know that this is this guy. Why? Because I saw them singing when I did the recording, that's all. I don't know any physics and nothing. I just know that this is this bird because I saw it. So I know which is the result. So I try with the initial distribution of values, and I get something different. I want to use this difference, the difference between this and this, and the difference between this and this, to change these values, and this is what backpropagation means. And in a number of iterates, you're guaranteed that this will work. So, does this mean that the scary artificial intelligence that will leave us out of jobs, all of us, is the chain rule? And the answer is yes. It's the chain rule. There is no more than that. Of course, and a lot of power, and a lot of electricity, and a lot of resources, and it's very interesting, this conversation, but mathematically, if you were working on field theory and string theory, and you were working in this math, now you go to Nobel Prize and become a billionaire with a chain rule. That's a fact. So, the same mechanism for training these networks is valid for very different architectures. And the people that were doing the exercises yesterday, we discussed the collapse where we were training the autoencoders. We didn't present the collapse for convolutional neural networks, and these are recurrent networks that, since as I mentioned before, is the grandma of the transformer that is feeding ChatGPT-4. So let's see, for example, what an autoencoder does. So an autoencoder, which I'm going to be describing when I do a more interesting talk on Thursday, is trained to do something that is really interesting. It is a symmetrical structure where you have a set of layers that are symmetric with respect to a middle layer, and the idea is that the training here is non-guided and works like this. You have an input that could be an image, so you have this number of pixels by this number of pixels arranged in a single vector, and you have this image converted into a vector, and you have this vector being fed into the first layer of this. And what you want is the autoencoder to just copy exactly the image that you had before. Exactly the same image. And you wonder why that would be of any interest, right? Because you could just feed, you can build the identity function, and you would have exactly that result. But now the trick is that you do it requesting here to have a number of units that is as small as possible. Now, why this isn't trivial? Imagine that if you want that each image is mapped uniquely into a copy of itself, you cannot have two images that are mapped to the same point in this low-dimensional representation, because if that was the case, then when you want to open it again, you wouldn't have a function. So if you have a representation where every image in your training set is mapped identically to itself, you cannot map two things into the same point. So what you have is, if you do it successfully, is a representation of your data that is one-to-one in this smaller dimensional space. So for example, if you have the movie of a labium of a bird that is singing, like we saw in the I guess that in the problem session yesterday. Okay, you have this moving, which is the minimum dimensionality that you would need in order to represent the dynamics. 2. Because if you have something that is oscillating, you cannot have a lower dimensional representation than 2. Okay? If I have something that is oscillating, my favorite example is a particle in a spring. You have a particle in a spring, and you take a picture, and you say, well, I measure the distance. Do I have the state represented? No, because I don't know if it's going to continue in one way or the other. I need to have also the velocity. So I need at least 2 variables in order to embed a periodic motion into a low-dimensional space. So if I try with 5, it will work. With 5, it will work. With 4, it will work. With 3, it would work. With 2, it would work. With 1, it won't work. The error will jump, because you cannot do a one-to-one representation into this space, if this is a movie of something that is oscillating, into something of dimension 1. And of course, if you have chaotic dynamics, which would be the minimum number of units that you could expect? 3. Okay? You have chaos, deterministic chaos cannot be embedded in 2 dimensions. You need 3, like in the Lorentz system, like in a forced periodically nonlinear Duffing oscillator, whatever. Okay? You have 3 variables in order to have something that is very messed up, but is completely deterministic. So if I have here a movie of something that is behaving chaotically, okay, like the image of a convection problem, you have the temperature and the velocity and have the movies there, okay? And you have the movies of this thing that is represented mathematically by the Lorentz equations. You have the 2 movies, okay? This is evolving chaotically. You know the Lorentz system, right? Who doesn't know what the Lorentz system is? Okay, so you have the movie that corresponds to chaotic convection, and you use each frame, and you train out encoder here to each image to be mapped exactly into itself. In here you will have a representation, a 3-dimensional representation of the data. Question, is it obvious that the topology of that complicated strange attractor is going to be the same as what happens is this low-dimensional representation? So the answer is no, it's not obvious, but we can prove, and we'll see that it is the case. So it's a wonderful way of taking a movie of a chaotic, complicated dynamics and having a low-dimensional representation. Now, do you have any idea what the variables mean in here? No way. It is non-interpretable. Can you do something about it? Well, this is an interesting question in itself. But the key of this is that instead of just saying, well, this is a chaotic problem, and I'm going to put the Navier-Stokes equations, and I'm going to have the modes of convection, I'm going to plug them into the partial differential equation. I will do the differential equations for the amplitudes of the mode, and I'm going to get the equations. That's interpretable science. Now I get a complicated flow, and I get a movie, and I get the flow by this. This is non-interpretable science. Now, is it the same science? Well, that's a question that we'll be continuing discussing. Here it is for the ones that were in the problem session, what the movie looks like. And the idea, for those that were in the first lecture, do you remember when I started this research program on birdsong, I conjectured that you would have relaxation oscillations in the motion of the labia 25 years before I could measure them. Okay, but when you measure them and you find the low-dimensional representation of that movie, what we'll see tomorrow, we will get something that is a relaxation oscillator. Okay? So it was a good guess. We're not going to be talking about convolutional neural networks. This is another architecture that I think is going to be useful for you to be familiar with. This is called a recurrent network. And these recurrent networks were specifically designed to correct a problem that these networks have when you want to process time series data. Remember that when we were discussing, I don't remember, it was so far away. oops, my God, here. When we're processing a time series data with this multi-layer perceptron, you don't use at all that there is a high correlation between the variables at different temporal instances. So you treat this set of data like if these values are completely independent, and if you have a long time series data, each segment is trained independently of the previous one. So this is good for processing time series data, but it's not efficient at all. So recurrent neural networks, which are now very much used in natural language models, were designed specifically to deal with time series data. And the idea is that you would have a unit that is the output, and you will have a recurrency. So you have a number of hidden units in here, and when you process it, you take a segment and you iterate a number of times that corresponds to the number of points in that segment. So at every instance, you are feeding this network with a new value of the segment in here, and what you want is that the final result is the prediction of the next point. So you create here a representation that has memory of the previous steps, and that had worked and ended up being a very efficient way of dealing with time series data. To have this iterative processing implies that it is equivalent to having just copies of this basic device, identical one after the other, so it ends up being a feed-forward network, but with just much smaller number of parameters, because it's the same block once repeated over and over. The interesting thing here is that it is successful in trying to predict the value of this time series data. So apparently, if you do a lot of interpretable science and compute differential equations and compute the flow is a function that, given an initial condition, gives you the next time in the evolution. So all that math that we did in interpretable science, this guy doing this processing and fed with backpropagation is equally successful in doing it. So the question is, where is it hiding the dynamics of the problem? And here there is a lot of interesting math that is still to be done. For example, a result that we published recently says that in here, in the number of hidden units, you also have a multi-dimensional representation of the data with the same topology, exactly like in the autoencoder. The only problem is that for the autoencoder, we could prove it mathematically. For this, it's still a mathematically open question. Okay, so why these things are doing the same things that we can do if we do dynamical systems, this is still an open question. So in these two classes, what I stressed is the differences between these two approaches. In interpretable science, you have interpretable variables that are related by interpretable mechanisms. And in data science, you have neither. Just a disclaimer, of course, interpretable science is data science because it's continuously fed by data and tested against data and so on. But you're constraining your explanations to the variables that you can measure, that you can imagine, that you can reconstruct. The basic idea in what we call generically data science is that you don't put yourself into those boundary conditions conceptually. So from now on, what we're going to see and what we're going to see tomorrow with different examples are the similarities. We will explore where does the dynamics hide in a neural network, particularly in the cases of the autoencoders and the recurrent neural networks. And I think that with this, I finish today's lecture. Thank you.